For a box placed on a horizontal surface, in many situations, the normal force is simply equal to the weight. But as we tilt that surface, the normal force begins to decrease, as is shown in these situations. The weight, of course, remains the same. You can't just tilt a surface and make weight change. But the normal force is what is affected by that angle. And we're going to take a look at mathematically why that occurs. We'll be looking at the components of the weight that are parallel and perpendicular to the surface. It's important to recognize why we're looking at those directions, at why we are taking something that seems perfectly fine, a vertical force, and breaking it into components. Okay, it's because the weight force, the gravitational force, does not point either parallel or perpendicular to the motion. The box, if we just place it on this incline, is going to slide along this direction, parallel, of course, to that surface. So that's going to need to be one of our axes. The other axis is going to have to be, by definition, perpendicular to it. So it's going to be something like this. So this will be sort of our new x and y axis, although you'll hear me call it the parallel and the perpendicular axis. Well, that means that the weight force does not point completely in either one of those directions. And so that's why we have to break that into components that are parallel and perpendicular to the incline. And what we notice is that as we tip the incline even greater, like this last picture, one of the components, the one down the incline, the parallel one, becomes much greater, and the other component, which will associate with the normal force, becomes smaller. The perpendicular component is decreasing, while the parallel component is increasing. So we might wonder, since it has that sort of relationship, does this have to do with sine and cosine? And it certainly does. We might hypothesize that since the sine function increases as theta increases, and this arrow increases in size as theta increases, does that parallel component have something to do with the sine? Absolutely. So let's take a look at how that happens here. Again, taking a look a little at some trigonometry. So here is just a single snapshot of a block on an incline with our two forces labeled, our weight force and our normal force. Now, of course, there could be other forces. There could be a friction. There could be some sort of applied force, tension in a rope or something. But these two forces are always going to be present if we have a mass on a surface that is inclined like this. Now, typically, the angle that we're given is this angle down here at the bottom of the incline. But that's actually not a good place to have that theta. We need to somehow connect that with the rest of the picture so that we can involve sines and cosines and so forth. With a little bit of geometry, it can be shown that that angle theta is the same up here as well. Real quickly, if we sort of sketch in a right triangle like this angle here would also be theta, and it would be a complementary angle to this angle up here. But this angle, maybe we'll call it phi or something. Phi and theta are also complements of each other over here as well. So that's how we can tell that the angle at the base down here must equal the angle over here as well. So that brings us to our final step. We can now come up with some expressions for the components of weight parallel to and perpendicular to the incline. If we are given an angle down here, and again, almost every time we will be, then mg times the cosine gives us the perpendicular component, and that will eventually be associated with the normal force. In many cases, it's what balances the normal force, so its value is equal to F sub n. The other component, which I guess some people might see sort of over here on the other side of the triangle, is pointed down the incline. And so mg times the sine of our angle theta will always have something to do with the object's actual motion, whether it is helping to slide it down or working against its motion as it moves up the incline. So again, the sine component will be related to the motion of the object, either helping or hurting the motion. And then the cosine will give us information related to the normal force. And so that's going to be important when there is friction in the problem. You should memorize these ideas. We should always be planning to make theta be that base angle, and we need to memorize that mg sine points down the incline. That almost rhymes. Mg sine points down the incline, and mg cosine is what we're going to use to figure out the normal force and to figure out friction. You can take a look at the other videos to see some examples of how these components can be used in action.